All right, moving on, let's get into our next topic, which is exponential functions. In problem 10, it wants us to analyze and graph the following function, f of x, which you can see here is an exponential function. It's equal to 3/2 times 4 to the x power. So we've talked about exponential models, right? Looking at f of x, right, equal to a times b to the x power. Well, with our base, b, we do have restrictions on our base. Right? It must be greater than 0. And it cannot equal 1 as we talk about the definition of an exponential model. Now, since this example here, our base is equal to 4. Right? Since that's greater than 1, that implies this is increasing, right, for all x. Right? And we know, again, this is of the form a to the x. So we got, or b to the x, I should say. We've got our increasing function. We have a horizontal asymptote at the x-axis. So again, this has a horizontal asymptote, which means it'll flatten out, approach the line y equals 0. So our horizontal asymptote, our exponential models of the form a times b to the x power. All right, whether that's b value being greater than 0 and less than 1, right, which are decreasing for all x, or like this is a case where it's greater than 1, right, in this example, since it's increasing for all x, it's still going to flatten out at the x-axis, which means we don't have any zeros. So if our horizontal asymptote, which they've asked us to write down over here to help us build our graph, is the line y equals 0, again, this is an imaginary line that shapes our graph. It's closer and closer and closer to it. So what's going to happen as we look at the graph of this function, as the x values get smaller, right, the outputs are going to get smaller and smaller. So as you go to negative infinity on the x-axis, you're going to see this graph getting closer and closer and closer to the x-axis, but never touching it. All right, it's an horizontal asymptote, and this function has no zeros to it. So there are no zeros with that horizontal asymptote at y equal to 0. Now our y-intercept point, if you remember, a value of a, right? A tells us our location of the y-intercept. So I'll make that note up here. Our y-intercept point is at point 0a. And we know why, right? We could find this algebraically, right? We could let x equal 0, right? So it implies find f of 0. Let's go ahead and do that together algebraically so we can show that characteristic. So out goes x, right? And in comes that input of 0. Let's put it in a different color. Anything we know raised to a power, a number like 4, raised to a power of 0, right? We know from exponent properties that simplifies to 1, which 3/2 times 1 is 3/2. So again, you get that value of a, right? And it's probably the coefficient of our exponential term, right? So that's our value of a. So that implies our y-intercept, right, is equal to the ordered pair 0, 3/2. So we know where it's going to cross through the y-axis. Now, 3/2, 1.5, 1.5, however you want to write that. But there's that value of a, right, in our example. Right? So I just want to show that characteristic with our exponential models. Now we know the domain of all exponentials is all real numbers, negative infinity to positive infinity. There's no undefined values. You can plug anything you want in x, you'll get an output. Our range on this function, since it's increasing for all x, we know it's going to be approaching the x-axis but never touch it. So our y values, so remember domain is x, range is y, it's going to be all y values greater than 0, 0 to infinity. So with that said, we can easily sketch, right, this graph. So let's start to build the graph here, this exponential model, using these characteristics from exponential. So again, let's go ahead and plot, or let's go ahead and label the horizontal asymptote y equals 0. So I'm going to dash in here in blue. right? Here's my horizontal asymptote. Here's y equal to 0. All right, and I'm going to go put in my y-intercept point. So let's let this be our ordered pair here of 0, 3/2. All right. And to give a little more detail, let's go ahead and find a couple other points. All right, so let's label a few more points here. So for example, we could let x equal, let's go make a table here. So with our x values and our y values. So we could let x be, for example, let's do negative, how about -1, right? You could plug that value in. Let's let x be -1, get a value on the negative side of the x-axis. What would y equal? So y would equal 3/2, right, times 4 to the -1 power. Well, we know from exponent properties, right, -1 power, that's same thing as reciprocating, right, flipping that would be the same thing as 1/4, right? So that's 3/2 times 1/4 as we flip that and reciprocate, right? And then what's 3/2 times 1/4? Well, as we simplify that down, that's 3/8. So -1 3/8. We could plot that point. So we'll put that ordered pair in here just to give some values. So again, give these points here, give a little detail, just some quick points to get. Now let's do a couple more on the right side of the x-axis. What about the x value of +1? What would you get? Y equal to 3/2 times 4 to the 1 power. And this 3/2 times 4. And of course 3/2 times 4, that's what, 12/2 or 6. All right, so as we simplify down, y coordinate is 6. So there's our y value. So we can plot that ordered pair. So that implies we have that point 1, 6, right, on our graph. So we'll go ahead and label that. Just again, give some more detail. So right 1 up 6. We'll put 1, 6 on here. All right, and we could keep doing that. I mean, we could let x be 2. We got a few points. Now, usually in ALEKS, if you're practicing your problems in your homework, right, or in your practice tests to build the exponentials, they'll usually ask for around 5 ordered pairs to plot along with the asymptote. And the key information is this asymptote. So as I graph this, right, I want you to notice, as I graph this function as it comes from -infinity, right? You're coming from the left side of this graph here. You're always increasing exponentially, right? Base 4. So there's our graph here, this model. Here's f of x equal to, what? 3/2 times 4 to the x power. So we can easily build this graph here of an exponential. There's two things you want to remember, and that's your horizontal asymptote and, of course, your y-intercept. Those are two quick things you can look at right from your model from the get-go. So again, with that said, you've got two cases. You can be increasing for all x, right, this one. You can also be decreasing for all x. And what happens with those graphs, right, if you were to look at decreasing, you have that with bases that are greater than 0 and less than 1. You'll have that kind of behavior going on. All right, so again, that's something I wanted to look at with us. Let's put that back in here. Drawing in this y-axis since I erased it. But I built that graph. So that's the exponential model, right? Looking at it increasing exponentially, base 4. So with that said, let's go to an application of an exponential model. Let's go to problem number 11. It says if $1,000 is invested into an account with an annual rate of 3.24% and no deposits or withdrawals are made, how much money is in the account after 8 years if interest is compounded semi-annually continuously. All right, well, let's look at our exponential model that defines this exponential growth here with compounding periods. So again, we're compounding it on a set number of periods. Well, that's given this model. So A of t be the amount after t years. So we'll let t be our time value, right? And A, again, the amount of money in 2 years, is equal to our principal, all right, times 1 plus our interest rate divided by n, which is the number of compounding periods in a year, raised to the power of nt. All right? So that's our compound interest, right, formula. So that's our exponential growth formula here in this problem as we're looking at an exponential model. So P being the principal, make a note of what everything is. And of course R equaling the interest rate, right? Which is our growth rate, right? In this growth model, this exponential model. And N representing the number of compounding periods. Per year. So if we talk about, for example, A, so we want to compound it semi-annually. So that means twice a year. So the number of compounding periods in 1 year is 2. We're going to compound it twice during the year if we're going to do it semi-annually. We know our interest rate, right? That was given to be 3.24%, which we'll go ahead and convert that over to a decimal, which is 0.0324. Put that in decimal form. And then we're talking about an initial investment. So what is P? Our principal, right? Our principal is our initial investment, what we take to the bank. We're going to take $1,000, invest it. So that'll be P, right? So we have everything we need to talk about the exponential model. So that implies A of t, the amount of money in 2 years, would be equal to 1,000 times 1 plus R over N, so 0.0324, divided by 2, semi-annually, compounded, raised to the nt power, right? Now N being what? 2, so 2t. So there's our exponential model. Now, with that said, we have the model here in front of us. Right? Let's go to finding the how much money is in the account after 8 years. Right, so they're giving us t. So let's go ahead and calculate that together. So after 8 years, that implies what? A of 8. So take out t, plug in 8. 1,000 times 1 plus 0.0324 divided by 2 raised to the 2 times 8 power, right, which is 16. So you can go ahead and simplify that if you want. But let's go ahead and type that in right now on our TI. So getting our calculator out, and if you want, we can put it in there together. All right, let's bring up the TI here. We'll go ahead and look at that on our calculator. So in here, let's go ahead and type it in here. So we got 1,000, right? Parentheses. Now we'll put in our, all right, 1 plus our base here, 1 plus R over N, 1 plus 0.0324, right, the interest rate, divided by the number of compounding periods in a year, which is 2. Close our parentheses, and we're going to raise that, right, to a power of 2 times 8, which is 16. So I'm going to put my exponent up in here, all right, and we can hit the enter button, and we'll get our output. So compounding this semi-annually, right, we're finding out, again, the amount of money in 2 years on this one. So we have 1,293.20, right, 0.2 years. So there's our amount of money there in 8 years. So let's go ahead and type that in there. That's approximately $1,293 $1,293.20. So we'll go to the nearest hundredth. So there it is. So amount of money in 8 years, compounded semi-annually at an interest rate of 3.24%. There's our funding. Now look at Part B. Now Part B wants us to find the amount of money in 8 years if we compound it continuously. So now we're not looking at a set number of periods during a year, right? We're not looking at that. We're looking at continuous model. Now a continuous model, that's our exponential model, base E. So A of T would be equal to P, my initial investment, times E to the RT. PERT. PERT's continuously. So the way to remember it, principal at base E, right? E is our natural number, right? 2.718. You look at it as a decimal, it's a rational number. You can look at your TI has your natural number E on there, so you work with that easily. But let's go ahead and find out what we would have in 8 years then. So after 8 years, right, that implies A of 8 equal to our principal, which was $1,000, times E to the RT, which is 0.0324 times 8. Right. So let's go see what we get. So there it is. We plugged it into our continuous model. So looking at it, growth here continuously instead of a set number of periods during the year, our compounding periods. So let's pull our calculator back up here and see what we get. And I'll show you again where E is here on the TI. So 1,000 times E. Now E, as you can see, is above here on the left-hand side of your calculator. You'll see the log key and the ln natural log key. Above your natural log key, you see E to the X command. So that'll allow you to put in your natural number E, which you want to do. You don't want to put in a decimal that's rounded. Make sure you're using E on your TI. And then it allows you to type in the exponent, which the exponent was 0.0324, right? We got to raise it to the R times T power as our rate as a decimal, times 8. So hitting the enter button, I've got 1295.89. Right, so after 8 years, if we compound the interest continuously, right, we'll have $1,295.89. So a set number of periods. Now let's look at problem number 12. A little different, but it is another compound interest problem, another exponential growth problem. If you want to have $1,000 in 10 years, so they're giving us our future amount, right? They're giving us A of T. So in 10 years, we're going to have $1,000. How much money do you need to invest in a savings account now that pays 2% interest compounded quarterly and continuously? So again, with this first bit of information, right, we know that A of 10, the amount of money in 10 years is going to be 1,000. All right, so they're giving us T and they're giving us A, the amount. All right, we know that our interest rate, R, is equal to 2%, which is a decimal is 0.02. And with that said, let's go ahead and write out our model. All right, now if we're looking at our first example, here we're setting a set number of periods to compound the interest. We're going to do it quarterly. Now with it quarterly, right, that would be 4 times a year. So N, the number of compounding periods during a year, will be 4. And again, we're looking at our model here with the quarterly. Let's go ahead and write out what the model will be. So A of T would be equal to our principal, our initial amount invested, all right, times 1 plus R. Well, R is 0.02, right, divided by N, which is 4, raised to the NT power, which is 4T. So there's our exponential model. Now let's go ahead and look at A of 10. So A of 10, well, A of 10, we know in 10 years, so again, I'm going to write that down. 10 years, we have $1,000. All right, so that implies 1,000 is equal to our principal, which we're trying to get, right? We want to know how much principal we have. That's the question. It says how much money you need to invest to get to $1,000 in 10 years with a 2% interest rate compounded quarterly. So times 1 plus 0.02 divided by 4, raised to the 4 times t power. Well, t is 10, right? So there's our value of t, right? And there's our amount of money, A. So plugging that into our model, you can see we've got a exponential equation to go solve. So if you're looking at this model here together, so we got 1,000, right, equal to P times 1 plus 0.02 divided by 4 raised to the 40th power. All right, now let's go ahead and solve for P. So if we were to solve for P, we would divide out this coefficient on both sides. So I'm going to let my calculator do the simplifying, but we're going to go ahead and divide this out. So 1 plus 0.02 over 4 raised to the 40th power. Now don't write that decimal in because you're doing rounding. We don't want to do any rounding to the end. Doing our algebra, we know how to isolate our variable, so we're solving for P. So as we're getting our value of P here, right, now we have what we want. So 1,000 divided by 1 plus 0.02, right, divided by 4, all raised to the 40th power. That equals our principal, our initial investment. So let's see what that is. Let's see what that will give us, all right, on this problem. All right, as we look at that, type it in. So 1,000 divided by, we got 0.02, 1 plus 0.02 divided by 4, right, raised to the 40th power there in the denominator. Right, so typing that in, checking it. Right, and what do we get? So doing it quarterly, as we round nearest hundred, $819.14. So 819.138. So there's our principal. So $819.14. Right, so solving that equation, right? Did a little algebra there on that one as we solve a linear equation. So let's go ahead and look at it continuously. All right, let's go do the same thing on our model. All right, now continuously, we're looking at what? What is our model here? So we got our exponential model. All right, A of t equal PERT. So again, that's when we're doing it continuously. Now, as we're looking at the amount of money in 10 years, so that would be $1,000 equal to our principal, which we don't know, we're trying to find based off compounded continuously. R, we got 0.02 times t. All right. Well, t is 10. So let's go ahead and plug 10 in. And as we solve that, right, we're going to divide out that coefficient on both sides. So let's go ahead and divide out e to the 0.02 times 10 on both sides of the equation. And then we get what we're looking for. So as we're looking at our value here, we've got P equal to 1,000 divided by e to the 0.02 times 10. All right, so let's see what we come up with. So what will our principal be on this one? So let's pull up our calculator again, and let's type that in together. See what we have here. So 1,000 divided by, remember, second natural log key is e, 0.02 times 10 here in the exponent, and end up with $818.73. 818.73. All right. So that's our growth model. So we talked about exponential growth, looking at it compounding at a set number of periods in the year or continuously. And you see that's using your different bases. If you've got a set number of periods in the year, you look at a base of 1 plus r over n. If it's continuously, your base of your exponential is the natural number e. All right, so I hope that helps. We'll take a break and continue on here in a little bit with some more examples.